Hello everyone, and thank you for being here today. My name is Peng from Zhejiang University. I'm excited to present my talk toward the high fidelity and real-time dynamic view synthesis. In this talk, I will present techniques that are pushing the boundaries of how we can generate dynamic views with high fidelity in real time. Throughout history, the way we capture and share our experience has evolved remarkably. We began with text, using the written word to document our lives and history. As technology progressed, voice recording allowed us to capture not just the text, but the emotion and intonation of the human voice. Then, images became the new standard, allowing us to preserve moments in visual form with photographs. Lastly, the video rises, enabling us to record and share our lives in motion, adding yet another layer of depth to our storytelling capabilities. And we currently capture our memories and experience predominantly through 2D video. This format has served as well, providing a single viewpoint from which we can relive moments. However, it's limited to the perspective from which it was recorded, facing us to one angle, one frame of reference. In contrast, the future lies in volumetric video. This innovative technology allows for multi-view capture, meaning life can be recorded from many angles simultaneously. These multiple perspectives are then used to create a 3D reconstruction of the event. With volumetric video, the end result is an immersive free viewpoint experience. Users can navigate around the scene, looking at the action from any angle they desire. Building on the concept of dynamic view synthesis, one of the most exciting applications we are seeing is immersive telepresence. This technology is showcased by Microsoft and Google. Is reshaping the way we think about remote interaction. Another significant application we are seeing is preview point broadcasting. This technology allows viewers to experience events from any angle they choose, providing a more immersive, interactive viewing experience. An additional application is recording our live and with true to life fidelity using technologies like Vision Pro. This tool is an exemplary stride forward in how we capture and preserve our daily experiences. Okay, and here are three important things for implementing a good volumetric video system. First, we need to easily capture volumetric video with phones or low-cost devices. Second, the rendering should be high quality. Third, the volumetric video should enable real-time rendering for interactive play. Okay, in the field of volumetric video, prior systems have largely fallen into two categories. The first category is use view interpretation. And this method relies on densely captured input views to interpret new viewpoints. However, the downside is clear. It requires a substantial amount of input data, and the range of output views it can generate is quite limited. The second category employs reconstruction technologies, as seen on the right. The systems require depth sensors to construct high-quality mesh models of target scenes. However, this method also comes with significant challenges. The quality of the reconstruction heavily depends on the input quality, and these systems often struggle with robustness and the ability to represent complex things accurately. Both the systems require complex hardware, which impedes easy capture of volumetric videos. In recent years, neural scene representation has become a popular method for modeling 3D scenes. A seminal work in this area is NERF. It uses MLP networks to record the scene. Okay, and NERF-based methods enables easy capture where we can reconstruct volumetric videos from multi-view videos like this. Based on NERF, there are two primary approaches to model dynamic 3D scenes. The first approach is to introduce an additional temporal dimension to the NERF framework, allowing for per-frame modeling of the dynamic scene content. This method adds a time variable to the input of the MLP network. The network then outputs the color and density for each specific frame in the sequence, effectively capturing the scene's evolution over time. The second approach involves defining a template nerve in a canonical space and then applying a deformation field to this template to recreate the 3D scene at different moments in the video sequence. The two approaches to dynamic scene modeling with neural radiance fields present here are pioneering efforts in these fields. However, they both encounter significant challenges. A common issue for both categories is limited rendering speed. The second issue pertains to the quality of real rendering. This method tends to produce poor rendering results on complex scenes. The third issue is that this method cannot handle large-scale scenes due to the memory limitation and poor quality. In this talk, I will present our progress towards high fidelity and real-time dynamic view sensing. To address these challenges of real rendering speed and poor rendering quality, we have introduced four methods to overcome these challenges. First, I will introduce enough, then M4D, and then 4K4D. Finally, strict Gaussians. Okay. As the first part of my talk, we are going to dive into enough. Enough is a pioneering work that marks the first to achieve real-time rendering of dynamic 3D scenes. As we have previously outlined, the current methods for modeling dynamic 3D scenes are faced with critical issues, including low rendering speed and poor rendering quality. Recent advancements in this field have seen the emergence of grid-based methods for dynamic 3D scene modeling. This method introduced the concept of defining feature plans within a grid structure to augment the descriptors of 3D points. The advantage of this approach is twofold. Firstly, it significantly increases the modeling capabilities. Secondly, it improves rendering speed by decreasing the size of MLP networks. Also, Kaplans have improved the rendering quality. The rendering quality they achieve is still not good enough, as shown by the right video. To overcome this problem, our idea is leveraging the rich information available from multiple perspectives over time to infer the colors of points within a scene. By analyzing features extracted from multi-view video frames at different time points, we can construct a high-quality appearance of dynamic 3D scenes. The key advantage of this method is the high rendering quality it achieves. By analyzing multiple input images, we can capture a more comprehensive representation of the scene, leading to a richer and more detailed rendering images. However, there is a trade-off. The downside to this approach is the low rendering speed. Processing multiple viewpoints to reconstruct a high-fidelity image requires significant computational resources and time. So, to overcome this challenge, we delve into an analysis of rendering costs associated with modeling 3D scenes. The rendering cost is a critical factor in evaluating the efficiency of 3D scene modeling. Is typically determined by two factors: the number of points of in a scene that need to be processed, and the per point cost, which is the computational expense of rendering each individual point. To optimize the rendering process, our idea is decreasing the number of sample points in the scene. Traditional method, as shown on the left typically sample points throughout the scene. This exhaustive approach can be computationally expensive and inefficient, as it processes many points that may not contribute significantly to the final image. And our method, as illustrated on the right, proposes a more selective sampling strategy. We we in we choose which points that are around the geometric surface of the scene, so we can reduce the computational burden. Specifically, our approach begins with the estimation of depths in novel set using the multi-view stereo technique. This technique is crucial as it allows us to capture the geometric detail of the scene from multiple viewpoints, thus enabling us to create a depth map. Once we have estimated the depth, we proceed to the rendering phase. Here, we use depth-guided sampling to significantly speed up the rendering process. This method leverages the depth information to efficiently sample the scene and render it quickly without compromising on quality. Here, we present the quantitative comparison across two different datasets. On the left, we have the performance metrics on the D2 dataset. On the right, the nerve synthetic datasets. On both datasets, enough producing comparative rendering quality while being able to render a much faster speed. Here are two quantitative results of our new rendering techniques. And we outperform ST-Nerve and Reality Works. Our technology also allows viewers to experience sports events from many angles, providing a more immersive and customizable viewing experience. Here are some results. We incorporate with a broadcasting company to obtain this data. Next, I will present the second part of this talk on 4D, which aims for better rendering quality. Although enough produces good performance, it still has some issues. The first limitation listed is multi-view inconsistency. Namely the problem of achieving consistent rendering quality when the scene is viewed from different angles. The second limitation is poor rendering quality on edge regions. This typically refers to a loss of detail or clarity at the boundaries of objects within a scene. The edges are often the most challenging areas to render accurately due to complex interaction of geometry. Let's revisit the two categories of 4D reconstruction methods: grid-based methods and multi-view IBR methods. As shown on the left, grid-based methods learn a global scene. On the right side, multi-view IBR methods infer point colors based on multiple input images. Grid-based methods can produce multi-view consistent results as they define global scene representations in 3D space. However, they may not deliver high quality when processing complex sequences, since the model capacity is limited. In contrast, multi-view IBR methods are capable of producing high-quality renderings that are rich in detail and appear very realistic, because the input images preserve high-fidelity appearance of the target scenes. However, they tend to suffer from inconsistencies when the scene is observed from varying angles because they predict the geometry and appearance of the scene in the view space. Okay, to solve this problem, we introduced M4D, an approach that aims to combine the strengths of both grid-based and multi-view image-based rendering methods to overcome their limitations. M4D represents the geometry of the scene as a global grid-based representation. This is motivated by that the inconsistency is generally caused by the incorrect prediction of the scene geometry at each view. By learning the global geometry at 3D space, we are able to achieve multi-view in consistent rendering. As shown on the bottom left, we represent the scene appearance with multiple images, considering the high rendering quality of multi-view IBM method. By doing so, our approach can produce multi-view consistent and high-quality rendering results. Here are qualitative comparisons on DNA rendering datasets. The rendering results of M4D appears to have better consistency and quality. The details, especially along the edges, are rendered with greater clarity, indicating that our method is successful in combining the strengths of both grid-based geometry and multi-view image-based appearance to produce a high-quality results. Here are Here are quantitative results on DNA rendering datasets. Our method consistently outperforms baseline methods in terms of all metrics. We can significantly improve the rendering speed of our methods by pre-computing the geometry field of the target scene in advance. Then, the cache geometry is used to guide the sampling process of volume rendering. Using this technique, M4D is shown to achieve 79 FPS on the ZGU mocap dataset, while ENUF achieves 51 FPS. Here are some quantitative results on DNA rendering datasets. DNA rendering datasets includes a wide range of human subjects and customs. The variety of clothing styles from casual to traditional clothes present different challenges for rendering, such as complex textures and forms. The results indicate the robustness of our rendering algorithm. We also show the capabilities of our method applied to different datasets, the inner outdoor datasets, and the neural 3D datasets. Now, I introduce the third part of this talk, 4K4D. This method combines the high-quality rendering of ENUF and M4D with even faster speeds, which obtains real-time rendering on 4K resolution on a consumer-grade GPU. Although ENUF and M4D produce impressive rendering performance, they are still not fast enough when dealing with high-resolution output. The ENUF method shows a low rendering speed of approximately 5 FPS on synthesizing 2K resolution images, which struggles that while it produces images that are perceptually close to the reference, it struggles with maintaining a high frame rate at high resolution. To further improve the rendering speed, we again analyze the cost of the rendering pipeline. The cost is typically determined by two factors: the sampling process, which is a critical step in rendering, where the algorithm decides which points in the scene to compute in order to create the final image, and the per point cost, which is the computational expense of rendering each individual point. By optimizing the sampling process and reducing the cost per point using machine learning, we can achieve high-quality rendering at a low computational cost, thereby increasing the rendering speed. To speed up the sampling process, we represent the scene geometry with a 4D point cloud representation, which supports the hardware rasterization. To reduce the per point cost, we propose a novel hybrid appearance, which enables the network pre-computation. With these two techniques, our method obtains a significant advancement in rendering speed. We obtain a real-time rendering performance even when synthesizing 4K resolution images. Here, I first introduce the geometry model. Our method represents the scene geometry using point cloud sequences. For a targeting, we extract the initial cloud sequence by applying the space carving algorithm or multi-view stereo algorithms. Then a 4D feature grid is predefined to assign a feature vector to each point, which is then fed into MLPs for the scene geometry and appearance. The geometry model is based on the point location, radius, and density, which forms a semi-transparent point cloud. The proposed representation can be rendered using the differentiable depth splitting algorithm, which supports the hardware rasterization. As shown in the figure, we use the image blending technique and the spherical harmonics model to build a hybrid appearance model, where the image blending technique represents the discrete view-dependent appearance and the SH model represents the continuous view-dependent appearance. IBR model has been widely used in previous methods. These models incorporate view directions as part of their input to render images. The network takes a set of inputs, each consisting of an image feature, a point feature, and a view direction. The network uses the view direction to adjust how pixel colors should be combined to produce a view-dependent blending weight. Because traditional IBR models use view direction as an integral part of their inputs, which necessitates network inference during rendering. And because there is a network inference during rendering, the rendering process is inevitably slow. And our solution is proposing a discrete IBR model, which is an alternative to traditional IBR models. The key difference is this new model is that it does not take view directions as input for the neural network, which could simplify the rendering process and enable pre-computation. We calculate the corresponding blending weights based on the point feature and the image feature. Therefore, the blending weight is independent from the viewing direction. To achieve the view-dependent effect, we select some near-east input views according to the viewing direction. Finally, the point color is computed as the weighted sum. Because these input views are obtained through the near-east neighbor retrieval, so our IBR model is discrete along the viewing direction. To achieve the continuous view-dependent effect, we append the 5-level color represented by the SH model as shown in the figure. Our method regresses the SH coefficient by passing the point feature from 4D feature grids into an MLP network. This is the overview of our proposed pipeline. Given the initial cloud sequence of the target scene, we define 4D feature grid to assign a feature vector to each point, which is then fed into MLPs for the scene geometry and appearance. The geometry model is based on the point location, radius, and density, which forms a semi-transparent point cloud. The appearance model consists of a piecewise constant IBR turn and a continuous SH model. The proposed representation is then from multi-view RGB videos through the differentiable depth splitting algorithm. Okay, next I will present some results of 4K4D. Here we present a quantitative comparison on enough outdoor. The results show that we achieve a significant high FPS, indicating a faster rendering time. Here is the quantitative comparison on DNA rendering. Because we only need to render foreground humans, our method achieves more than 200 FPS. Here is another comparison on Neo 3DV dataset. We again significantly outperform previous methods. Okay, we also compare our method with 3D Gaussians. Our method works well on the enough outdoor datasets. In contrast, 3D GS offers the training views and fails to generalize to null views. Compared to training a 3D GIS for every frame, our method is superior in the following ways. First, the storage cost for 3D GIS is too large for even a 100 frame video, while our method maintains a reasonable 2 MB per frame storage overhead. Second, the hybrid image-based appearance model of our method is more expressive than the spherical harmonics highlighted by 3D GIS, thus achieving higher rendering quality as shown by this figure. We also perform ablation studies to validate the effectiveness of the proposed component. The table shows that the complete model generally performs better than the versions without specific components, indicating that each component contributes to the performance of the model. Here we visualize the output of SH model. The view-dependent SH color compensates for the high quality but discrete IBR color. It provides the fine-level appearance that enables the continuous view-dependent effects. Here is a qualitative comparison between our method and guidelines. As shown by the results, our method is much better than previous methods. And here is our comparison with our method and enough. We also present more quantitative results. As shown, this thing is complex because there are many peoples and they occluded each other. And here are more results. This data is captured by ourselves. Okay, finally, I will introduce the last part of this talk, strict Gaussians. This method extends dynamic radiance fields to large-scale urban scenes. Existing nerve-based methods has limited capacity due to the MLP network, so they cannot handle large-scale things as shown in the right figure. To solve this problem, we replace nerve with 3D Gaussians. The 3D GIS has the higher quality, fast rendering, and fast training as shown in their original paper. And we just replace the nerve with 3D GIS, and we find 3D GIS can model the unbounded scene in high fidelity. And to represent dynamic cars, we use a set of checked boxes for modeling them. So the dynamic urban scenes are represented by compositional 3D GIS. And here we use a static background model, 3D GIS model, and a set of dynamic 3D object model, 3D GIS object model to represent the dynamic scenes. An additional change is the captured data has varying illumination, as shown by this figure, because this car is moving, so the lighting on its surface is varying. So to solve this problem, we add time basis to the spherical harmonics function, which thus can model dynamics appearance. As we can see, with the dynamic appearance model, the rendering quality improves much. The bottom left is our result, and the bottom middle is the model result for this spherical harmonics model. Here is the quantitative comparison on the Waymo dataset. As shown in this figure, our results outperforms previous methods significantly, and we also has a much better FPS. And we also compare with recent um, a recent enough method. As we can see, our rendering quality is much better than enough. Okay, here are more rendering results. Our method is robust to various things. And not these results are not GT videos. They are render results. And our method can also be used for some applications, such as we can remove the background and obtain the foreground object. Second, we can edit the scene because we can decompose foreground object from the scenes, so we can add them into the scene. Okay, in summary, in this talk, I have present our progress towards high fidelity and real-time dynamic view synthesis. And the four works the four work have solved the challenges, including low rendering speeds, poor rendering quality, and limited scene scale. In the first work, enough is the first method that achieves dynamic view in real time. And the second work, M4D, achieves better rendering quality. And the third work, 4K4D, is the first method that achieves real-time rendering in 4K resolution. And the last work, 3 Gaussians, it achieves high rendering quality on large-scale dynamic urban scenes. Also, we have solved some problems in the field. There are still many problems to be solved. Our goal is making volumetric videos accessible to every end users. And to achieve this goal, there are still many challenges to, to overcome. The challenges are summarized into four main areas. The first challenge is how to develop a more diverse and easier to use capture devices. This suggests the need for a range of devices that can accommodate different scenarios and user skill levels, making the technology more accessible to a broader audience. And the second change is how to reconstruct volumetric faster from images. Faster reconstruction is important because improving the speed at reconstructing volumetric video, it will reduce the cost and is essential for many real-time applications. The third challenge is to enable the storage of volumetric data on mobile phones. In the future, if we want to spread the volumetric video, the most convenient device is mobile phones or VR devices. So the storage of these videos should be able to be small enough to be stored in these devices. So we need to develop some efficient data encoding technology that allow high volume 3D data to be saved. And the final challenge is to ensure the volumetric video can be displayed like a 2D video, supporting real-time decoding and rendering. This would allow users to interact with volumetric videos similar to the traditional videos, making the technology seamlessly and user-friendly. Okay, thank you for your watching. This is all my reports.